Ready, okay. I'll talk about the joint work with S.Shadrin and B.Vallette. And yeah, so I will talk about some quite nice algebraic varieties that share a lot in common with Deligne Mumford compactifications of moduli spaces of genus zero curves with marked points. And well, what exactly are similarities that they share? I will try to explain along the way as I'll recall some the picture in which the Mumford spaces are involved. I will then tell you what the spaces that we are considering are and discuss their geometry and maybe in the end talk about potential applications. So somehow what this story is slightly missing is striking application. So it is it looks like certainly a cool definition that should be out there, but most applications are still one more of conjectural level. And how do I don't know what it doesn't really want to turn. Okay, so let me remind you about the classical picture in particular. I want to I'll mention right away why in the title of the talk I write M0 and +1, not M0n. Because, well, my original motivation comes from operad theory, and so you view those Deligne Mumford spaces as a topological operad, where you think of one of the n+1 points as the output of an operation and the rest as inputs. So M0 and +1 parameterize some sort of n-ary operation. So this guy is the linear compactification, and as I said, it has an operad structure, and the way this compactification works is that it has a very nice stratification where the boundary strata are made of products of smaller M0 k+1 bar, and this somehow gives you essentially an operad structure just by inclusion of boundary strata. So that's what the one important piece to remember from the classical story. And now there is this diagram which somehow is what ultimately I want to a generalization or an analog of which I want to explain to you. So it has this collection of the Mumford spaces, which has an operad structure. It has each of these has as an open piece M0 and +1, and this collection of spaces doesn't form an operad, but it's still nice in many other ways. Then there is the operad of framed little two disks. And the operad of little two disks. And, little two disks are indeed parameterized as configurations of n little disks inside the big one with an obvious operad structure. And framed, as usual, means that you also mark a point on the boundary of each one, and this gives you another operad, another topological operad. And of course, there is an inclusion of little two disks into framed little two disks where all the framing are just trivial at the point 0 on the circle, angle 0 on the circle, then if you take the quotient of little two disks by the rotation, you get something which is homotopy equivalent to M0 and plus 1. Well, because somehow a disk with n holes is essentially the same as the sphere with n plus 1 holes, but up to this rotation which you kill here. And a slightly less, or maybe much less trivial result is that the homotopy quotient of framed little disks by the action of the circle is represented by the Deligne Mumford operator. And this is a much more interesting statement in any way. So it was probably first stated in some way by Kontsevich in Hodge Memorial Lecture, and well, on the topological level, probably the only rigorous proof that I am aware of was produced by G.Horel, Drummond Co. This diagram has an algebraic counterpart somehow, which, unlike the previous one, where in the bottom left corner you don't have an operad, here you have actually 4 operads. The operad hyperhom, which is the homology operad of the Deligne Mumford operad, and it controls genus 0 level of homological field theory. The operad BV of battalion-Minkowski algebras, the operad of controlling Gerstenheimer algebras, and, well, up to some suspension, the gravity operad first considered by Ezra Getzler, and these things. So in the top row, there is again some sort of homotopy quotient by the delta operator in BV. Gerstenheimer operad is included in BV. The operatic suspension of gravity is included in Gerstenheimer, and these two operads are related by causal duality. So somehow there is this this sort of diagram on the algebraic level. Yeah. Sorry?
About n equal 1 for m 0 and plus 1 bar.
You mean operations of arity 1? Well, all these operads are connected, so the unit operations are just one-dimensional as the identity. Oh, sorry. Yes, not for B. Not for B.
For hyperhom you don't take that. Because there is an option of taking M0 2 and interpret the CP infinity or something.
No.
Huh?
Yes.
Okay. No, you can do that or that. I was which one.
Yeah. And in particular, this result with the about the homotopy quotient is interesting for one extra reason, which also probably was some motivation for Kontsevich to have claimed that homotopy quotient result on the topological level is that using this homotopy quotient result, it is possible to interpret the Givental action on hypercommutative algebra structures on a given vector space, on a given chain complex, as change of trivialization of the homotopy circle action. And this somehow is a rather important fact that that sheds some extra light on the Givental group action, and I will get back to that a little bit later. So this Givental action, it allows to encode some familiar things like BV algebras and what is called commutative homotopy BV algebras in terms in terms of geometry and intersection theory on Deligne Mumford spaces. So, well, BV algebras can be viewed as commutative algebras with an differential operator of order at most 2 that squares to 0. Commutative homotopy BV algebras have collections of operators of various orders which satisfy certain relations. And the order of a differential operator can be encoded in terms of the so-called causal braces, and it turns out that the causal braces somehow inside them have all the intersection theory of the Mumford spaces. And this is something that myself, S.Shadrin and B.Vallette noticed in 2011, and that was some starting point of various things that we've been working on. Now, motivation for the story I want to tell you about came from a little preprint of Kai Bergersen, who used to be a PhD student of Sergei Merkulov in Stockholm. So in 2013, he put a preprint on the archive where he explained that if you have an associative algebra and an operator on it that squares to 0, not necessarily a derivation, then from the data you can obtain some sort of an infinite algebra structure on the suspension of A. And the formulas that he, first of all, this result is quite similar to a more classical result for commutative algebras, where an operator on a commutative algebra that squares to 0 can be used to obtain a Lie infinity algebra structure on the suspension. And in that case, you indeed use the causal braces, and Bergersen's formulas somehow suggested that one has some maybe non-commutative causal braces in some way. And our attempt to understand those non-commutative causal braces somehow brought us to the story I want to tell you about. So what I mean to say is that Bergersen's formulas suggested that there should be somehow a diagram like that, where I just essentially copied the diagram that we had before, and just I added NC instead of every operand name, meaning that there is something non-commutative happening here. So Bergersen, in fact, defined implicitly or explicitly within his preprint what should be non-commutative versions of BV and of Gerstenheimer. And quite interestingly, his NC Gerstenheimer already appeared before in work of Victor Ginsburg and Travis Shadler on what they call non-commutative deformation theory, the situation where the deformation parameter does not necessarily commute with the algebra that you are trying to deform. So they produced a chain complex that controls such deformations, and that complex naturally has a structure of this non-commutative Gerstenheimer algebra. So somehow this part of the diagram was when we started thinking about what was already there. What was happening here was not so clear, but at least we somehow knew that if we wanted to mimic this, we should take the homotopy quotient by delta and so on, and doing homotopical algebra for operads is something, well, that I know how to do. And so the algebraic part of this diagram we recovered sort of easily. I will not tell you right away what the result is, because I want to first tell you about the geometry and then explain how the algebra that we recovered here actually naturally comes from geometry. It is a much nicer way to do that. So geometrically, indeed, the computations that we did on the algebraic level suggested that there should be some sort of diagram, and at least from if we want to obtain algebraic thing as taking homology of the geometric thing, we somehow knew what most of the things that should be here, that the non-commutative Gerstenhaber in arity n was behaving like just a product of n-1 copies of the circle. Non-commutative BV in arity n was behaving like a product as 2n-1 copies of the circle. And non-commutative gravity in arity n was behaving like a product of n-2 copies of the circle. So that's, and then there was something completely mysterious here, not completely mysterious, some topological space whose homology was concentrated in even homological degrees, and altogether the Betti numbers in arity n would add up to the nth Catalan number. That was what we knew at that point. Now, it was the non-commutative Gerstenhaber is a very easy operator, and it was incredibly easy to guess what kind of topological operator you should get to obtain non-commutative Gerstenhaber as homology. In fact, there is a sort of general construction that takes a topological space M and cooks an operator out of it, which somehow generalizes the associative operator. You get the associative operator when the topological space is a point, and otherwise you get something a little bit less obvious. So you put in arity n the product of n-1 copies of m, and operator structure is just obtained by insertion. Okay, so here I+1 should be I. So basically, to compose a k tuple with an l tuple at the ith place, you just put the l tuple after place I-1 unchanged. So this is somehow a very trivial operator structure, and if your topological space is the circle, you obtain an operator whose homology is non-commutative Gerstenhaber. Also, if your topological space is a circle, then circle acts on this, circle as a group acts in this operator. And there is a standard construction of a semi-direct product operator in the category of G spaces with G. And if you do this semi-direct product, you obtain an operator whose homology is NCBV. Well, this is. Oh, that's right. So these operands, they are all non-symmetric. So if you want to make a symmetric operand, you just take the adjoint of the forgetful puncture, you symmetrize forcefully, but they are non-symmetric, like the associative operand is. Okay, so this bit with the product of n-2 copies of the circle, I'll get back to that in a few minutes and explain why it really belongs in this corner of the diagram. But now I want to explain what happens in the top left corner. So, so now let me give you a definition of what we had to call the brick operator, because these spaces that I am going to explain appeared recently in a completely different context in work of Laura Escobar, who did her PhD with Alan Knudsen studying subword complexes for Coxeter groups and so on. So she defined in much higher generality what she called brick manifolds. So there is some sort of combinatorics which where you see some sort of bricks arising there. Those guys are honest algebraic varieties, and a little joke I tell every time I talk about this, that presumably she decided to call it brick manifolds because when you type brick variety in Google, Google brings you construction companies that sell different varieties of bricks, and if you type brick manifolds, it gets more mathematical. So in any case, let me give you the corresponding definition. So first of all, I start with this with the underlying combinatorics, and the underlying combinatorics are these directed graphs like this. So you start with just two disjoint points, then you put 3 points and 2 points and put arrows up like this, then you put 4 points, 3 points, 2 points, and put arrows like that, and it is very easy to extend this pattern. Now I want to take such a diagram and decorate it with some vector spaces. Namely, if I have n points in the bottom row, I take the vector space of dimension n-1, which I number by gaps between the points, so to say. I put the e12, e23, en-1n. Then I put the subspaces of this space at vertices of the diagram, so that the following condition holds: that on the left slope I put the standard flag of V, so I put the span of the first vector, span of the first two, span of the first three, and so on. On the right slope I put the opposite flag. I put the span of the last one, span of the last two, and so on. And altogether, I want to ensure, the conditions are that in the row I, all the subspaces that I put are I-dimensional, and if you have an arrow between the two vertices, then the corresponding subspaces must be included in one another. So not only I put flags here and here, but there should be some inclusions. For 2 points, it's a one-dimensional space, so nothing really happens. Yeah. On the next slide, I have several examples. So P of 2 is indeed a point, because there were no choices. P of 3, there is only one choice, what to put here. And this should be a one-dimensional space of the two-dimensional, so P of 3 is just P1. Now let me discuss two different ways to construct B of 4. So we already have the standard flag here, the opposite flag here, so if we have these U1, U2, and U3. Now, let's start with bottom up. So if you choose U1 and U2 generically, then U3 is the two-dimensional subspace where we know two one-dimensional spaces inside, and so if we chose them generically, then U3 is reconstructed uniquely as the direct sum of U1 and U2. But the only way when we cannot reconstruct them is when U1 is the same subspace as U2. U1 is a subspace of the two-dimensional space spanned by E12 and E23, and U2 is the subspace of E23 and E34. So the only way for them to coincide is to be the subspace spanned by E23. That's the intersection of these two guys. And if they coincide and equal to the subspace spanned by E23, then there is P1 choices for U3. So what you have to do, you have to take the product of P1 cross P1 and blow it up at one point. So that's the what BF4 is. However, I want to also mention another way to reconstruct BF4. If you take U3, then if U3 is generic, then you reconstruct U1 and U2 quite trivially as the intersection of U23 with this left coordinate subspace and the intersection with this right coordinate subspace. And then you can ask yourself when this reconstruction is not unique, when either U3 is equal to this guy or U3 is equal to this guy. No. It's a 1 hour talk. Right. And so you get the blow up of P2 at two different points. And well, this is one easy and standard exercise of any introductory algebraic geometry course, that these two guys are indeed the same. Okay. Now, generally, both of these approaches works, and B of n can be obtained either as an iterated blow-up of of the product of n-2 copies of P1 or of Pn-2. And this somehow should be reminiscent of construction of two different constructions of Deligne Mumford spaces due to Kiel and to Capel. So somehow, so far so good, there is some sort of similarity. Now, unlike Deligne Mumford spaces, these Bns are also toric varieties, because there is a rather obvious action of the n-1 dimensional torus rescaling individual basis vectors of V. There is a one-dimensional torus which stabilizes everything where you rescale them by the same constant, and so you have n-2 dimensional torus which quite obviously acts with an open orbit, because if you in the bottom row, if you don't choose at each place a coordinate subspace as your one-dimensional subspace, you can reconstruct everything uniquely. And so, because of this, because it is toric, it has an open piece C star to the power n-2, which up to homotopy is the same as the product of n-2 circles, which was what we wanted in the diagram that I was showing you. We wanted to have some sort of open piece, some replacement for M0 n+1, which is homotopy equivalent to the product of n-2 circles. So again, so far, everything works fine. Now, let me tell you, this maybe is the central part of the talk for the purpose of this conference. Let me tell you about the stratification of these guys, which somehow lead to an operant structure, lead to an understanding of intersection theory, and so on. So, open strata of B of n correspond to planar rooted trees with n leaves in a rather nice and simple way. So somehow, if you take some tree T with n leaves, there are just two constraints that constrain the subspaces that are allowed for points of that open strata. Namely, if you take, let's take some edge of the tree, which is not a leaf. So from that edge, you have a subtree growing where the smallest leaf is labeled L, and the largest is labeled R, and L is less than R. Then you just put so the first condition is somehow a closed condition, even though it's an open stratum. So the closed condition is that in row R minus L, you say that subspaces number L and number L+1 are both equal to this particular coordinate subspace. And another condition is an open condition. So if you have if you have any particular edge, it can be a leaf or not a leaf, and L and R are again the smallest and the largest leaf in the subtree growing from there, then in row R minus L+1, you say that the Lth subspace must be different from two possible coordinate subspaces. So you throw away two possibilities. And somehow it turns out that this leads to a very nice stratification of these guys. So let me give you two statements, two examples of strata. So first of all, if you take the tree T, which is just a corolla, so just one vertex from a few leaves sticking out of it, this just encodes the open stratum because the first condition is empty. There are no edges which are non-leaf edges, and condition 2 just prohibits two possible coordinate spaces, and so you get the open stratum here. Moreover, if you take a slightly more complicated guy, if you take a tree with just one internal edge, then an inspection of these two conditions would say that the corresponding stratum is just the product of two open strata in the for smaller arities. And okay, now there are these crucial products of this stratification. So first of all, in fact, every stratum is just a product of several copies of C stars, and in fact, it just comes from the fact that this stratification, as I defined, it is obviously compatible with the torus action on, and so it is stratification by torus orbits. So somehow it is very much compatible with the torus structure. Then, of course, yes, it is a stratification. So B of n is the disjoint union of all these guys, and this is really important, that the closure of every stratum is a union of strata where for all trees that are obtained from the tree T by expanding edges, or alternatively, so T is obtained from T prime by contracting some internal edges. So somehow this hints at a very strong operatic structure behind all of it. In fact, if you look at closed strata, you also have the corresponding statements about products which mimic what I said before for the open strata. Moreover, examining the geometry of the strata, one can immediately see that the break manifold is a smooth compactification of the open stratum, and the complement normal crossing divisor. And in fact, this also can be obtained. This result can be obtained in a different way. So, usual Deligne Mumford spaces are, among other things, wonderful models for for Coxeter arrangements. Wonderful models in the sense of the Concinian Pachesi. And in fact, in this particular situation, the corresponding result is also true. These guys are wonderful models for certain subspace arrangements, but instead of the Coxeter arrangement where you remove all the diagonals, you take some kind of non-symmetric version of the Coxeter arrangements where you remove only the adjacent diagonals, xi equal to xi plus 1. So from the point of view of subspace arrangements, xi equals to xi plus 1, this collection of subspaces it's a rather trivial one, because there are very few of them. It's not the most exciting example for people who do wonderful models, but it turns out that it still leads to some interesting thing which somehow has a lot of nice geometric properties. Now, let me, as I told you, in the first place, we computed the algebraic version of the story and computed the algebraic operand, which is the homology of something, and then we discovered that something. So let me now explain what happens on the algebraic level. There are many different maps from B of n to P1 to projectivization of two adjacent basis elements, EI minus 1i and EI plus 1. And somehow you can you can examine the preimages of different points. Those preimages must represent the same homology class. And if you look at the preimage of the first base coordinate subspace, you get the union of all strata like that, where you have trees with one internal edge, where the left or the smallest leaf on the top, it has number I. And if you take the preimage of the second coordinate subspace, you get the strata corresponding to trees with one internal edge, where the maximal leaf on top is leaf number I. And somehow, because preimages of 2 points represent the same homology class, you get this sort of relation for every I, which should resemble the relation relations in the Deligne Mumford homology of Deligne Mumford operator, where you have relations for every 3 leaves, not necessarily 3 adjacent leaves. But here we work with the non-symmetric operator, so it's not too surprising that you obtain things with adjacent leaves. So there is some sort of generalization of associativity. So if you start with if you write this relation in RT3, it will be precisely the associativity. If you go higher up, you get some generalized associativity. So somehow non-symmetric version of the operator hypercommon. And it is possible to prove that there are no other relations, but this requires some preliminary algebraic work that we did studying the corresponding operator algebraic. Now, let me say a few words about the interception theory. So first of all, if you take 2 different strata, well, there are, of course, 3 possibilities that they intersect transversely, do not intersect, and intersect non-transversely, but it is, these situations is sort of easy to describe in terms of combinatorics of trees. So 2 strata intersect transversely if there is a tree from which both T1 and T2 can be obtained by contracting edges, and you contract disjoint sets of edges. They do not intersect if such a tree T does not exist, and intersect non-transversely if some of the edges that you contract are the same for T1 and for T2. Because of that, intersection theory is essentially reduced by some operatic argument, is reduced to computing self-intersections of the strata corresponding to trees with 1 internal edge. And it turns out that all intersection theory can be encoded by analogs of psi classes on Deligne Mumford spaces. So for Deligne Mumford spaces, of course, there are just topological line bundles corresponding to various marked points. And here there are nice line bundles that I'm going to define here. Of course, the only thing which is missing so far in this picture, and will be missing until the end of this talk, that even though I'm talking about some non-commutative M0 and bar, I don't have any non-commutative curves with non-commutative marked points, so you cannot really talk about line bundle at some point and so on. But somehow nice line bundles still do exist. So first of all, there is a line bundle which we define, which we call L naught. So we take the top part of the diagram. So we know that in the top 2 vertices you just have the n-dimensional vector space, n-1 dimensional vector space n-1. Here you have the previous subspace of the standard flag, here the previous subspace of the opposite flag, and so here you have one specific n-2 dimensional subspace U. And if you take so you can take the quotient Cn-1 by U, and this will be the fiber at the corresponding point. And L1, Ln, you look at the bottom row of the diagram where you have n one-dimensional subspaces, and somehow you say that the fiber of Li at this point, given by this configuration of subspaces, is Ui star. So it's important to take the star. Well, so basically what you want to take the pullback of O of 1 under the map from Bn to the projective line that I mentioned in one of the previous slides here. And then somehow it turns out that there are some sort of non-commutative version of the topological recursion relations. So somehow you can express these psi classes as in terms of Poincare duals of the fundamental classes of the boundary strata, and so you have this relation which is valid for every I. So psi 0 is equal to the sum of Poincare duals of strata corresponding to trees with 1 internal edge, where both leaves I and I+1 are on the top part of the tree. And for every j, you can represent the psi class number j in two different ways like this. Somehow, when you deal with Deligne Mumford spaces, you can encode all the interception theory in terms of correlators of psi classes. And here, so in the case of genus 0 Deligne Mumford spaces, the correlators are multinomial coefficients. And here, in fact, so all non-commutative multinomial coefficients are equal to either 0 or 1. And there is a very simple combinatorial rule to say when such a correlator is non-zero. So intersection theory is much, much simpler and nicer here. Let's say that if we want to push all that analogy even further, we can say that genus 0 non-commutative cohomological field theory is an algebra over this over the homology of the Greek opera. And it turns out that in this case also you have the Givental action on structures of such an algebra, and this action also can be defined in a very similar way using intersection theory on these spaces. So somehow to give a structure of an algebra over this opera, you need to know maps from homology of P of n to multilinear maps on A. It's the same, of course, as in the classical case, as the collection of classes, of cohomology classes with values in multilinear maps. And then it turns out that you can, so you take the Lie algebra of linear maps of A with coefficients in, formal power series with coefficients in linear maps, and you define the action of Rkz to the power k on this collection of classes in this way. So you multiply in various places by psi classes and pre-compose or post-compose with this Rk. So there is this kind of map, and it's not at all obvious that this is a Lie algebra action, that it takes a homological, non-commutative homological field theory into a homological field theory, but just studying the, just using the properties of psi classes and of intersections of strata, it is quite easy to establish that yes, indeed, this formula actually specifies all these properties. This is somehow, on the one hand, looks like quite a bit of a miracle. On the other hand, maybe suggests that all these constructions in some way make sense, because formulas like that don't really pop up randomly.
Isn't there an argument to say that something is homotopy proportional to the other one, and the section is just the choice of the...
Yes.
It's the same reason.
Yes, but you know, the thing that the statement of the the statement of the on the homotopy quotient is also quite a bit of a miracle. For example, on the geometric level, we still don't know if it is true and why it is true. On the algebraic level, it is possible indeed to prove that a non-commutative hypercom is the homotopy quotient of an CBV by the operator delta. On the geometric level, it is a bit more mysterious, in fact. Finally, let me mention the issues of formality here, which for some of these operads turned out to be easy and follow from some standard arguments, and in one case was quite tricky. So somehow these three operas, which are the protagonists of this story, because, well, as in the classical case, the fourth operad, the gravity operad, is obtained as by a slightly more complicated means from something which topologically is not an operad. So questions of formality make sense just for these three operas, because these these really are obtained as homology of topological operas. Gravity is obtained by some sort of usual Poincaré residue thing, and so of something which is not entirely operatic on the. Sorry?
The question makes sense.
Well, yeah. So the last one, the NC hypercom, is formal for a standard reason, because it is an operad in the category of compact Kähler manifolds, and there is some the way you prove formality for the Deligne Mumford operad actually just follows through without any problem. The N+1 opera is formal also for a very silly reason, because it turns out that this operad, the generalization of the associative operad constructed out of our topological space M, because the operatic structure is so simple, it is just formal for any M. So there are absolutely no constraints here. And this is a rather easy argument. But for NCBV, it is much less obvious. And somehow the only argument that we now are aware of goes as follows. So first of all, you replace circle by C star, because it's a little bit nicer to work with complex manifolds. And then there is a very recent result of G.Horel from maybe a month and a half ago, which, well, no, I mean, it's a simple observation, but to prove it carefully, you really need, yeah.
Because I have the same for first algebras.
Yeah, of course.
You have to write it down carefully, otherwise it's wrong. But
yeah, no, but somehow I fully agree. And for associative algebras, some of the steps that you need for operas are not needed. So the situation is a bit simpler. Yeah. So I mean, for associative algebras, it has been recently rediscovered and reproved by Clément Dupont and so on. But in the case of operas, you really need to do some rather exotic yoga of infinity categories to invert some things. Well, I mean, we can discuss it later, but as of now, I don't know how to avoid some very unpleasant bits in this argument. No, in any case, for everyone else who haven't yet proved this, let me just state this argument, state the general result. So suppose that you have an operad in the category of smooth complex varieties, for which the kth cohomology of every O of n has a pure Hodge structure of weight 2k. So alternatively, you can do it of weight k. So you can do it either sort of on the sort of closed purity or open purity in a way. And in any case, if the Hodge structure is pure on one of the extremal points where it can be, then such an operad O is formal. And somehow a sort of naive, well, simple part is that to understand this, you play around with logarithmic gram complexes for various compactifications of O, but somehow the problem is that some of the arrows, if you notice that some of the arrows go in the directions where you don't want them to go, and you need to invert some quasi-isomorphisms, and then when you start doing it carefully, you need some unpleasant technicalities. But in any case, this is almost everything that I wanted to say. The only thing, as I said, that on the side of noncommutative BV and noncommutative Gestenhalber, we have some interesting examples of algebras over these operas, which come from noncommutative deformation theory, which come from some non-commutative formalism for differential operators and so on. On the side of NC hypercom, for the moment, we have some conjectures and some hope that mostly coming from moduli spaces of quiver representations, and so our hope is that interesting algebras over NC hypercom are somehow related to quiver moduli and Donaldson-Thomas business rather than Gromov-Witten business. But this is somehow at this stage is more of a conjecture and hope, and maybe in next meeting like that I will be able to say more about it. Right. I'll stop here and thank you for your patience.
There are questions for the speaker.
One thing you can say about little disks is that the algebraic varieties are interesting theoretically, meaning that, for example, the Hodge structure of the fundamental group is interesting, and the periodic. How interesting is this Hodge theoretically? Is it more simple or?
It's much more simple.
Okay.
Yes.
So there are no multiple zeta values or polylogarithms?
No, unfortunately not. Well, here what plays the role of little disks is just a product of circles. So all the things you can think of are very trivial.
Maybe another question. So you have this operator for any m. What are the algebras of this operator? This should be obvious.
Sorry?
You have this operator, this stupid operator we define for every topological space.
Yes.
What are the algebras over it?
Yeah, the algebras are so you have many binary products indexed by homology classes of M, and they satisfy some kind of mixed associativity between them.
And then what?
Well,
just all associative, and that's it. Right?
Yes, yeah. So it's just a very simple generalization of associativity.
It's just a family of associative factors.
Yeah.